series, and this is the main topic actually that I want to introduce today. One of the main concepts that I want to emphasize in this series of talks, but I want to start this lecture by thanking Damian and Spriat for taking me for virtually every beer place in Wroclow, and apologize for the other if I will be less coherent today than usual. Now here's the definition. Let S be S on X elevate action. Let me assume right away that it's Ergodic, even though this is not needed for the definition. Let G be an algebraic group now this is over fixed throughout this lecture series. Algebraic closed field complete with absolute value k, which will not appear anymore. This is in the background. So somehow we have left-hand side ergodic theory. On the right-hand side, I'm having algebraic geometry or algebraic groups, and I'm having a connection between the two. Let rho be an algebraic representation of S. So in other words, this just is a continuous homomorphism. And most of the time I will also assume some irreducibility. But it is the risky dense. This is not really needed in everything that will follow, but let me just assume it. So this is an algebraic representation of a group. So just presenting an abstract group, topological, but with no algebraic structure on it, into an algebraic group. It's like taking nice clothes and putting on this naked group. And also I want to do this for this ergodic space. And this would be an algebraic representation of that ergodic action. So you want basically to find an algebraic point representing this one. So here it comes, an algebraic representation of X, of the action to be precise, is a rho equivariant map. And by map I mean, well, I'm having this rho here, and I'm having the action of X here, and maybe just into some algebraic action of G acting on V, as this diagram shows. So G is acting on V, and now I want to find a map phi, which commutes everything. And of course, by map I mean various adjectives that are implicit. This is the Lebesgue space, this is the Borel space, and this is the map that we consider between such spaces. So where V is S equivariant, or O equivariant if you wish, Borel defined up to null sets, as usual. So again, this is putting algebraic laws on that naked value. A morphism, so such a representation is an object, naturally, in the category of such. A morphism of algebraic representation is...
And when you say S equivariant and whatever, well, it's just clear to the first. But when you say it's defined up to a null set, then you know
So,
S equivariance is like point lots of conditional values, and then up to a null set when you modify it, what does it mean up to a null set?
so there is an S invariant null set on X that I'm allowed to omit whenever I'm having such a thing. When you vary V and take, I don't know, another V1, another representation, those two representations, the map from X to V is not everywhere defined. It may not be defined on some S invariant subset of.
But S equivariance is strict.
S equivariant is strict.
Okay.
And actually, in the back of my mind, there is a theorem that says that whenever you have equivariance, which is defined almost everywhere, but the acting group is LCSE, then it could be promote to an actual everywhere equivariance. For this, if you haven't seen this before, there is the book on Ergodic theory and algebraic group by Zimmer, and there is a very clear appendix making all those things very, very precise. But I will not do it now here as precise as you might wish, because if I do so, I will not do it. Sorry? I intend to give a reference by the end of the next talk. Ergodic theory. I think it's called semi-simple groups and ergodic. But by the end of next talk, I will give a full list of references and some historical overview, which I'm trying not to do while presenting the map. Okay, so so far I explained what an algebraic representation of an ergodic action is, and let me emphasize, I don't have colors here, but let me emphasize that in this rectangle, 3 out of 4 things are fixed. This action is fixed, this group is fixed, this arrow actually is fixed, and what I'm varying is the pair V and phi. This is varying. Every such V and phi give another algebraic representation, obviously. And the morphism of algebraic representation should be something between these V and phis. So is a triangle, if you wish. So I'm having X, I'm having V, maybe I'm having another line, V prime, here is V prime, fitting into this, and a morphism should be a map here, name for this one, I don't know, alpha. Alpha is an algebraic morphism, so it's a morphism of algebraic variety, which is G equivariant. So it is happening on the right-hand side of the world. This half is algebraic, this half here is ergodic theoretical, and the morphism, well, and of course, and commuting, yes, let me, and alpha composed phi prime is phi. And this equation should be read up to null sets. This is equation of Borel maps defined up to null sets.
But does the commutation of this diagram do not imply?
Yeah, this is the commutation. Yeah, I didn't say, I didn't try.
And I mean G equivariance, because you have this action of S on X, and then
Yes,
phi,
it does imply.
and then rho of S is realistically closed. So by looking at all those diagrams,
So it does imply equivariance on the essential image of X. A priori, they might be bigger. I mean, there might be parts of V that does not see the image of X.
no,
If X is a risky density in V, it does it.
okay.
But I mean, I think it is easier to understand when I write this way. So these are the objects of this talk, of the lecture today. I hope the concepts are clear, and let me now give maybe an exercise before proceeding into slightly deeper things, just to build some understanding. This is an exercise for you. Assume X is S mod T, and S acts on it on the left. I wrote it on the right, I guess, but S acts on it on the left. Show that for every algebraic representation X to V, the following holds. The following diagram holds. So I'm having X to V on one hand. This is the given one, but actually I'm having some canonical representation of X, and this is G modulo the closure of this subgroup. I'm claiming that there exists such a thing. Just take rho, the equivariant map from S to G, and divide G by the Zariski closure of the image of T over there, and this map will fix the identity map of S. Oh, sorry, then this map will be T invariant on the right, so it will define a map from S mod T to that space. So this is an exercise for you to see, but actually further I want to say, if you have an S equivalent map here, the image of the base point, T, should be T fixed. And also fixed by the closure of T, so you will have a map here. There will be a unique such thing. So I said enough about it. It is left as an exercise to you to complete more words, put more words into it. The next theorem I want to present is related. So now what I'm about to do is to present a generalization of the result we've seen in the first day. At the first day, we consider maps, let me remind you, we consider maps from R2 to R2, or maybe I can just as well write C2 here, and the image which was SL2Z invariant, equivariant. We consider such maps, and observe that they're actually SL2R equivariant, and there were scalar multiplications. Do you remember this? And so we had some nice discussion about it. But what were we actually using? The essence of it is here in the theorem. So G will be SLNC. This is the group acting here. In that talk it was out, but I could have made C2. And S will be SLNR. Gamma in S, a lattice, and rho will be the inclusion. Of gamma in S in G. And by the way, we know this is a risky dance by Borel dancing theorem. Let now gamma act on x, and x is S mod t. Okay. Now t in S non-compact. Any non-compact. And now I'm presenting this gamma space X, not the S space, but the gamma space. Then, any algebraic representation of X, so X to V, now we have gamma of, maybe, of the gamma space X. Is actually S equivariant. A priori, I'm assuming only gamma equivariancy, but actually it's S equivariant. And if this is S equivariant, then I can apply this exercise, and actually we have X goes to V here, and of course we have the map G to the Zariski closure of T here, and this last thing follows from the exercise, given that result. Actually, I will not give you now the full proof of this. I will explain how to prove it. I will give you, we will recall some facts from last time, and then I will explain how to prove it using the same tools that we had, we developed at the first lectures. So we all know all the ideas somehow. I just need to collect it together for you. So let us recall things from last talk. If G acts on V algebraically, L in G any group, and mu is any probability measure, and if mu times mu is ergodic, it's L ergodic, then mu is delta V for some V which is L invariant. This is something we proved. Just make the remark. If point is L invariant, then it's also invariant. So it's a closure. Let me now state a corollary. Somehow I wanted to do it at the end of last talk and got confused. A corollary of this. For this specific setting, actually the setting might be more general than I'm stating. I don't want to get us confused with general semi-simple groups, etc. But you will see how I proceed. Take now specifically S to be SLN R. T inside S non-compact. And gamma inside S allies. Take G, algebraic, and now I want to map T. I'll use the same symbol, wrong. This will be an algebraic representation. Then every algebraic representation or every T, maybe a raw algebraic representation of S mod gamma is essentially constant. And let me put it again in a diagrammatic way, similar to this one, and to, what should be another one, and to that one. So you have S mod gamma, and you find a map, this is a T map, into some V. And the claim, I think now the claim should be clear. But maybe before completing this thing with data, let me explain. I'm using this fact that we have here. And the fact that we proved earlier in one of our discussions that the action of L on this is doubly ergodic, of T. The action of a non-compact group on such a thing, this was in our discussion of metric godicity, etc. The action on T here is doubly ergodic. I'm using it, and I'm using the statement that we put yesterday to conclude that the image here is a point. So there will be a point here that actually we are going to. Okay? And now, okay, so this is the corollary. We know this. I claim that the corollary implies that theorem, not right away, but we know how to. We discussed in the past this, I call it duality principle, of taking what is we consider at the theorem, we consider X S mod T, and we consider gamma equivariant map from S mod T. And somehow we massage such maps into T equivariant maps from S mod gamma. Do you remember we had this trick? We had this duality trick. If you have S mod T gamma map to V, we took it into a gamma map, a T map from S mod gamma to V. Somehow, if this map is phi, this is gamma map, we call it for some reason big phi. This was a T map. And the trick was to look at, I'm reminding now a trick, so this is not very formal. So we had a map S2V if X inside S mod T a base point, T point, say, I defined a new map sending little s here to S phi S inverse x. And we observe that such a map is, by the gamma equivariancy of phi, of little phi, it is gamma invariant. So it factors through S mod gamma, and this is the map phi, which will happen to be a T map, by the fact that little s, little x is T fixed. Then this, you see, you can read that this is a T map, and this is how you go, the duality goes. And then, when you prove the theorem, you start with some map phi, and you turn it into a map big phi, but this one must be constant, and you read what you get, and you get the result. I will not, so the proof of the theorem to complete it, since I will not use it, I will leave it as an exercise for you. But again, if you're lost, just look what we did in the first day. It is one by one this in slightly more general setting. Okay, so where am I heading? Apart of that, this is an interesting theorem. It was already interesting in a very special case, I find. We see here three very similar phenomena. This exercise here says that for transitive actions, whenever we have an algebraic morphism of x, there is this canonical object, canonical algebraic morphism. Okay, this is phi. Let's call this one phi 0. This one is canonical, and there is there exists a unique map from here to there. From this specific one to every general one. We have, and this map, of course, is a morphism of algebraic representation. There we have a very similar situation in a slightly more general, or slightly more complicated setting. This is a theorem, this is just an exercise. But again, we have this canonical representation of phi 0, and for every arbitrary representation, there exists a unique map from here to there. And we have another, somehow a bit trivial, but very interesting as well. This is just an expression of what we proved last time. But whenever you have a representation, now a T representation of S mod gamma, we have this canonical, let's call it phi 0, I don't know, this canonical map into a point, and there exists a unique, think of this occlusion as a map between the point variety into that variety. And of course this is equivariant, because this point is fixed. So all these are very similar, and I want now to state it as a theorem, a general fact. Theorem, important one, I'll make one, read it as I should. So again, let S on X be an ergodic action. להאמין כאילו זה נקרא גרופ, etc. etc. Then there exists an algebraic sub H in G and an algebraic representation from X to is G mod H. The point here is G mod G. From X to G mod H, such that phi 0 is an initial object in the category of algebraic reps of X. And let me explain what I mean by this, but this is the ladder you see. So, for every algebraic rep, X goes to V, we have and now I will draw instead of writing, but to be clear. Here is phi, here is G mod H, this is phi naught, and exists a unique morphism such that, of course, I mean, by morphism I mean with all the adjectives here, this is G map between varieties, and this commutes. Okay, and the proof of it is very, very easy. So I will give it now. Any questions so far? Can you repeat?
It suggests that phi sub-0 depends on phi.
No. Look, read the quantifiers. So, I mean, I didn't prove it yet. The claim is that there exists a phi sub 0 which does not. I mean, you say by that my example maybe it suggests. I don't know, but the fact is that this is the case. Maybe I will prove it in a minute, but before this, let me state something which, if you like, the jargon of category theory, this is a formulation of a unique lemma. But in any case, this is something very, very nice application of this theorem. Corollary or application, which is useful sometimes. There is a natural map from homomorphism of groups from the automorphism, the gamma automorphism of X under the base space, to the automorphisms of G mod H for this specific H as a G space for the algebraic automorphisms, which we've discussed. This is the same as the normalizer of H mod H. Yes?
And the side should be automorphisms as an S space, not as a gamma space.
So this is just the naturality or the universality of this initial object, let me very briefly explain this. So, explanation. So we have this map from X to G on H. This is phi 0. And assume I'm having an automorphism from X to X. So note, in the left-hand side category, I can look at phi 0 again, and I can think of this composed map as a new map into G mod H. And that diagram, for taking this to be phi, if you wish, in here, guarantees such a thing. So this would be, I don't know, a map. Depends on that W, or star of W. Let's call this star. And by uniqueness properties, etc., you check that it's actually a homomorphism. If I'm having another one, W prime, and I compose it, blah, 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 then things should get together well. So I leave it to you to check it's actually a homomorphism. This all star that I just defined. So this is useful. Things in many applications, I will use these two more. This observation are actually in slightly more general setting. And now I want to prove that theory. And so let me start by finding this H. And I will use a trick that we had before. Fix H minimal in the collection H in G at Y such that there exists but I can represent X in it. This is a non-empty collection. Can you see one element which is obviously there? G itself, right? I can always map to the one point. So this is a non-empty collection, and by notoriety, I have a minimal H. This would be the H of the music. And fix, now, then there might be more than one maps from this X to this G mod H. Somehow, every automorphism here will give one, every automorphism of that one will give another. Fix one. Fix one, call it phi naught. And now I need to show existence of uniqueness. Existence of uniqueness of such map. We will show existence leaving uniqueness as an exercise. But I just remarked about uniqueness. Once you have such a map, I want to claim this unique because of equivariancy and because this space is transitive. Okay, so equivariant map between transitive spaces are uniquely defined by the image of one point. And I know, take a generic point here in X, I know it goes here. Fix one point in X, which is well defined. Okay, so I leave this. And now I just have to argue that for every B, assume given is given. And I want to complete the diagram, as in here. Again. So again, I will use same tricks. We have a not very rich toolbox. I will use the same tricks over and over again. I'm having V here, I'm having G mod H there, I'm having X here in the corner in the far left, and I'm having this phi and this phi naught. And I want to connect. Now there is an intermediate space that projects into both G mod H time V. I'm having, I should have colors. These two colors are one type of maps, but all these are morphism for algebraic varieties, G morphism for algebraic varieties. And the thing is that obviously I have a map. Well, I'm having a map from X to here, right? To this algebraic variety. But the G action here is tail. We know this is an algebraic variety, and X is ergodic. When I map it equivariantly, it must hit one orbit. It cannot leave one various orbits. An ergodic measure on an algebraic variety should be supported on one orbit. This is something we were using again and again. So actually, there is one orbit here. Let me call it G mod H prime for some H prime that I will be mapped to. Okay, this is push, yeah? I hope this is clear. And obviously, now I can just look at this diagram and have this. But now we should think of the way we've chosen H. H was minimal. But if you have a map from G mod H prime, so first of all, phi prime is a representation of X into G mod H prime. H prime appears here. It's not here. But after conjugation, H prime is inside H, right? It's smaller, but not strictly smaller, because of the minimality of H. This actually must be an isomorphism. So this is by minimality of H. And now I can just go back on this, from here, go down here, and other there. This is my arrow between G mod H. Okay? And I just put the distance. This is everything. Any question? So, I should give a list of examples, but 3 examples already appear on the board. Maybe I should okay. Okay. In the next hour, maybe I should say what we'll do in the next hour. In the next hour, we will show that, or maybe here, we show that if you have a lot of ergodicity, if if T here acts too ergodically on this space, then the initial object is actually trivial. Sometimes I want to have situation in which I know that the initial object is non-trivial. And there is a gadget in analysis that does it for me. And this will come from transcendental methods. It's called amenability. We'll show that if an action is amenable as an action, then the initial object is non-trivial. This I will do next time, in the next hour. I will not define amenability of an action. I will take like an ad hoc way of saying this and some specific example of that will be used later. Okay, so let's take it.